Can
We
you
can see your page.
Yep, excellent. Thanks for preemptively telling me that. That's awesome. Okay, so today we're learning a few new things, but mostly well, subtraction is one of them, but we're on the same path as we were the second part yesterday, adding and subtracting vectors. And the video you're watching is also on adding vectors. It's just being applied to forces. And even if you haven't taken physics, I think you'll find it really straightforward. It's really just an application of adding vectors. So we're going to look at adding two vectors and finding the resultant magnitude and direction, using trig where necessary. Keep working on using proper vector notation. If you've taken physics, that's probably going to be one of the most challenging things for you to do. So how to subtract two vectors by adding the opposite. Given two unit vectors, we can find the sum or difference of scalar multiples of the unit vectors using proper vector notation again. And simplify a vector expression by applying properties of vectors. And we're going to start learning about the 3D just really briefly in this geometric vectors unit. And then once we start algebraic vectors, we'll mostly just be in 3D. Okay, so recall that to add two vectors, you must place them tip to tail. The sum is the vector that goes from the tail of the first one to the tip of the second. And then to subtract two vectors, you add the opposite. The opposite of a vector we defined yesterday to be a vector that has the exact same magnitude or size, but the direction is opposite. So here's our first question. Given vectors u and v, where the magnitude of vector u is 7 and the magnitude of vector v is 4.4, sketch vector u plus v and determine the magnitude of vector u plus v. That's how you would read that question out loud. So if you see, we've got vector u and vector v tail to tail, and the angle between them is 43. But when we add them, we have to add them tip to tail. So I'm going to move vector v so that it's at the tip of vector u. So I'm going to try to make it look parallel and the same length. And it's just vector v still, so I'm going to label it vector v. And then vector u plus v is going to have its tail at the tail of u and its tip at the tip of vector v. And then I'm going to make sure I have arrows on all of my vectors. And then I'm going to label this vector u plus v. And all they want me to find is the magnitude of vector u plus v after I've sketched the vector. So to find the magnitude, well, I know the magnitude of vector u is 7, so I know the length of this side. And I know the magnitude of vector v is 4.4, so I know the length of that side. So I would be able to use the cosine law if I knew the angle in between them. And because these are parallel, the C pattern says that this angle and that angle add up to 180 degrees. So this angle that I need to know is going to be 180 degrees, subtract 43 degrees, which is going to be 137 degrees. So now I can use the cosine law. So, and I want to use vector notation when I'm using the cosine law. So remember, this is, I'll just write the cosine law up here so you can refer to it if you're a bit rusty. So this is if you want to find the length of a certain side of a triangle, it equals the sum of the squares of the other two sides minus twice the other two sides multiplied by the cosine of the angle between the other sides. Now we're going to apply that to finding the magnitude of vector u plus v. And since I'm following the cosine law, squared is equal to, so the magnitude of vector u, so 7 squared plus the magnitude of vector v, which is 4.4 squared, minus 2 times 7 times 4.4 times the cosine of 137 degrees. And then we want to square root both sides. So we end up with the magnitude of vector u plus v is approximately, and we want to put that in our calculator. So I'm starting with the square root. Some of you might end with the square root, depending on your calculator, how it works. Cosine of 137. Another bracket to close the beginning one. Approximately 10.6 units. So we can see that's our answer. And since it didn't ask me for the direction, it just asked me for the magnitude, I would be done question A at that time. Any questions for this one? Okay. Part B, sketch vector u minus v, vector v, and find the magnitude of u minus v. So I'm going to refer back to this diagram and try to draw it, redraw it here. So I had vector u was horizontal, and vector v was at an angle of 43 degrees and shorter. So this is my initial diagram they gave me again, where this was 43 degrees. So this time I want to find vector u, subtract vector v. So remember when we added vector v, we just moved it here. So again, we're going to subtract also tip to tail, but the opposite of vector v is going to be the same length, but this direction. So I'm going to just come to the tip of vector u, and I'm going to stay parallel, but I'm going to draw towards downward, but parallel, the same length approximately that I see there. And so this vector here, when you're labeling it, be careful, it's negative vector v, because it's the same magnitude as vector v, but the opposite direction. So this is vector u, and then I'm subtracting vector v, and the resultant of that is going to start at the tail of vector u and end at the tip of vector v, vector negative v, my bad. And it's got an arrow. And then this side is going to be called vector u minus v. So I've labeled the three sides with vectors. This is vector u, vector negative v, and vector u minus v. And I want to find the magnitude of vector u minus v. I know the magnitude of vector u from the previous question was 7. Who thinks they know the magnitude of negative vector v? Anyone?
Is it negative 7 or negative 4.4 or negative? Yeah.
Okay, I'm glad you said that because that's the common mistake. So the magnitude of a vector is its length. So it's positive 4.4. Okay, so the length of this vector is 4.4 units. So that's really important to know that the length is not negative. Okay, that has to do with direction, having to be in the opposite direction, not the magnitude or the size of it. So we know these two lengths. So it'd be nice if we knew this angle. And because these are parallel, vector v and negative vector v are parallel, we have this Z pattern. And with a Z pattern, the angles in kind of like under the Z's, under the underarms of the Z's are equal. So that means this angle here is also 43 degrees. So we've got the magnitude of this side, the magnitude of this side, and the angle between them. So again, we're set up to use cosine law to find the magnitude of vector u minus v. So the magnitude of vector u minus v squared is equal to, so 7 squared plus 4.4 squared minus 2 times 7 times 4.4 times the cosine of 43 degrees. And then square root both sides. So the magnitude of vector u minus v is approximately so square root of 7 squared plus 4.4 squared minus 2 times 7 times 4.4 times the cos of 43 bracket. So you get approximately 4.8 units. So that's how you subtract vectors. Add the opposite direction. Okay, moving on then to question 2. Given that the magnitude of vector A is 5 and the magnitude of vector B is 7, and the angle between vector A and vector B is 70 degrees, find the magnitude of 3A minus 2B, include a label diagram with your solution. So I'm going to start off just drawing vector A and vector B tail to tail with an angle of 70 degrees between them. It's my initial diagram, I'll call it. So I know A is shorter. So there's my vector A, and B is longer and at 70 degrees. Maybe about that. So here's my vector A and my vector B, and the angle between them when they're tail to tail is 70 degrees. And I want to draw the vector 3A minus 2B. So 3A is going to be 3 times as long as A. So I'm just going to extend this vector so it looks 3 times as long and call it vector 3A. And then I want to subtract vector 2 times vector B. So subtract, I'm going to still be parallel, but in the opposite direction. So, and twice as long. It's about twice as long, maybe. So this is negative 2 vector B. And then my resultant vector is going to start at the tail of vector 3A. And end at the tip of vector negative 2B. So this vector here is 3A minus 2B. Notice that I don't have any magnitude bars when I'm labeling my vector diagram, because these are all vectors. They both have a magnitude and direction. So I don't have absolute value bars around my labeling in the diagram, which is a common mistake that students make. But it probably would be helpful for me to list out maybe up here that the magnitude of 3 vector A is going to be 15, 5 times 3. And the magnitude of negative 2B, it's going to be twice as long as vector B, so 14. And then we do know this angle again because these are parallel, these vectors. So again, I set up this Z pattern. So there's one arm of my Z, and there's the other parallel arm of my Z, which makes those two angles equal. So if that angle is 70, then this angle in here is 70 degrees as well. And they want the magnitude only of vector 3a minus 2b. So we know the side, angle, side, so we can use cosine law. So the magnitude of vector 3a minus 2b squared is equal to 15 squared plus 14 squared, subtract 2 times 15 times 14 times the cosine of 70 degrees, using the cosine law. And then square root both sides. And then go to our calculator. So I got approximately 16.7 units. Did you guys get that answer?
Yep.
Awesome. Yep. Okay, good. All right, so again, how do you draw the vector diagram properly, label it properly, and then use proper vector notation with the cosine law? Subtracting vectors versus adding vectors. Those are the big things for this unit on geometric vectors, which is just yesterday and today. All right. Question 3, given two unit vectors, u hat and v hat, and the angle between them is 62 degrees, find the magnitude of 7u hat plus 2v hat, include a labeled diagram with your solution. All right, so what can you guys tell me about the magnitude of vector u hat?
That's 1 unit.
It's 1. So anytime you see a unit vector, it's got that special hat instead of an arrow. And a unit vector is a vector that has a length of 1 unit. So for my initial diagram, I'm going to draw vector u and vector v tail to tail, 1 unit each, so pretty small. There's u hat. And at 62 degrees to that, I've got v hat. Make them look the same length if you can. So here's u hat, and here's v hat, and they're at 62 degrees. And I want to draw a vector 7u hat plus 2v hat. Someone's got their microphone on, guys.
I keep on forgetting to turn it off. I'm sorry.
It's okay. It's okay. So 7u hat's going to be 7 times as long as u hat. So I'm going to draw it's 7u hat like this. Just approximate here. I'm going to say that's 7u hat. 7u hat. And then we're adding 2v hat, so adding is going to have the same direction, not the opposite direction, and be twice as long. So 1, 2. So this is 2v hat. And then I want to show vector 7u hat plus 2v hat, so it's going to start at the tail of 7 u hat and go to the tip of 2 v hat. Arrow, and then label it 7 u hat plus 2 v hat. So there's my labeled vector diagram. In order to find the magnitude of 7 u hat plus 2 v hat, well, I know the magnitude of 7 u hat is 7 units because it's just 7 times the magnitude of u hat, which is 1 unit. And the magnitude of 2 v hat is 2 units. So I need this angle here. And since v hat and 2 v hat are parallel, it creates this C pattern here. So that angle is going to be 180 degrees minus 62 degrees, which is 118 degrees. So now I've got all the information I need to find the magnitude of that vector 7 u hat plus 2 v hat using the cosine law. So the magnitude of vector 7 u hat plus 2 v hat squared is equal to 7 squared plus 2 squared minus 2 times 7 times 2 times the cosine of 118 degrees. Go to my calculator. For that one, I got 8.1 approximately units. And again, it just asked me for the magnitude. So once you've done that, that's your answer. You've done your labeled diagram with your calculation using proper vector notation. Okay, now we have another question. This one's application question of displacement. So a bird travels 45 kilometers south, 23 degrees east. So again, I'm gonna start with the compass because I like to do that. So south, 23 degrees east, and then west. So here's my compass. So this is north, east, south, and west. And this says 45 kilometers south first, and then 23 degrees towards east. Remember, 45 is halfway, so it's going to be closer to south than east. And this vector is going to be longer than the next one. Keep that in mind. So I'm going to draw this a representative sketch here. And that'll be my vector. And then I want to label it. So I'm going to turn my paper sideways to label this vector. So this vector I've drawn is 45 kilometers. And then in square brackets, I put the direction. South, 23 degrees east. And then it turns and travels 32 kilometers west, 30 degrees south. So for me, I need to put another compass here. That helps me a lot. So I'm gonna, at the tip of this vector, I'm gonna put in a north, south, east, west compass. Remember, this is north. So I wanna draw a vector that is west 30 degrees south. So that means mostly in the west direction. 30 degrees towards the south, which again isn't halfway. And the vector is going to be shorter. It's going to be 32 instead of 45 long. So I'm going to say, feel comfortable with that representing the vector there. And then I'm going to label this vector 32 kilometers west, 30 degrees towards the south. So I've added the vectors tip to tail, and now I need to draw the displacement vector, which is going to start at the tail of the first vector and end at the tip of the second. And it's got an arrow, and we're calling it displacement. So I do know that I know this side is, or this vector is 45 kilometers long, and this vector is 32 kilometers long. And to get my angle, well, so I know this little angle in here is 23 degrees. And I can do a Z pattern. So straight south along the vector to straight north means this angle in here is also 23 degrees. So the angle between the vector and north. But I know that a whole quadrant is 90. So from west to north is 90. So this piece in here is going to be 90 minus 23. Does that make sense to everybody? If this little piece in here is 23, then this piece is going to be 90 minus 23, which is 67 degrees. And then this little piece in here, well, we know this angle is first west and then 30 degrees towards the south. So this little piece in here is 30, which means the angle between these two vectors is 67 plus 30, or 97 degrees. Finding the angles is probably the most challenging part of this first intro to vector stuff. You have to remember the C patterns, the Z patterns, complementary angles. And now you've got your side angle side, you can find the magnitude of the displacement vector. So you're going to use the cosine law. The magnitude of the displacement vector squared is equal to 45 squared plus 32 squared minus 2 times 45 times 32 times the cosine of 97 degrees. Square root both sides. And I got 58.3 kilometers for the magnitude of my displacement. However, displacement is a vector. Got a symbol, vector symbol over top. So that means unless it just asks me for the magnitude, I also have to find the direction. So I want to say what direction this displacement vector is in. So I can see from my diagram, like if I've drawn it correctly, it looks like it's going to end up being south so many degrees toward the west. We'll see. But it's going to involve us wanting to know this whole angle here, which I'm going to call theta. So if I want to find angle theta, I can use the sine law if I have a side angle pair, and I do because now I know the length of the displacement vector and I know the angle opposite. So I'm going to say that the sine of angle theta divided by 32 is equal to the sine of 97 degrees divided by 58 point, and I usually use more decimal places. I got 0.309 here just to try to be as accurate as possible in calculating the angle. And you can jump straight to the answer, but again, for the first time today, we're using the sine law, so I'll show the steps algebraically. So I would multiply both sides by 32. And then this gives me the sine of theta, but I want angle theta. So to do that, I take the sine inverse, which looks like sine. It looks like it has an exponent of -1, but that just means inverse. Input that into my calculator. Using like second sign or shift sign, depending on your calculator. Make sure you're in degrees. And I got that angle's 33 degrees. So that means this whole angle from the displacement vector to the 45-kilometer vector is 33 degrees. So how does that help me determine the direction in like the compass direction, north, south, east, west for the displacement vector? I know its magnitude is 58.3 kilometers. Who knows what its direction would be?
What if the, oh, Jared, you can answer if you want. I don't know if you,
Go for it, John.
okay, all right. I think it'd be south 10 degrees west.
Yes, very good. South 10 degrees west. So if this whole angle is 33, 23 degrees is taken up by this part of the angle here. So that means that this little piece here is 10 degrees. So that means the bird's displacement from the middle of the compass here is in the direction south 10 degrees towards the west. So the bird from its starting position has landed or stopped 58.3 kilometers south 10 degrees west from its initial starting point. And that's what displacement means. Okay, so again, one of the biggest mistakes is for someone to write that the direction is south 33 degrees west, but that's not right. You have to look at your diagram and make the angle you're finding make sense with the information you're given in the question. All right. All right, number 5. There is one like this on the assignment today. So if vector u is a magnitude of 4 and vector v is a magnitude of 5, then vector u minus v has a magnitude of 6, find the magnitude of vector u plus v. Any ideas how you would even start a question like this?
You could try drawing the triangle of vector u, vector v, and vector u minus v.
Yes. Okay, so I know vector u is shorter by a little bit, so I'm going to start off with vector u. And I'm not given the angle, so I'm going to guess. I might have to redraw my picture afterwards, but I'm going to guess for now. And v is going to be a bit longer. Does that look a bit longer? No, not really. Okay, so I don't know. So I'm guessing for now, this is my vector u, this is my vector v, and then vector u minus v. is going to be the same parallel, but the opposite direction. Okay, so an important thing here. I know the magnitude of vector u, I know all these three magnitudes. So I have to calculate an angle because I know all three sides of the triangle. Now, you always want to use the cosine law to find the largest angle because it's the only angle that could be greater than 90 degrees. Okay, every triangle could only have a maximum of one obtuse angle, and cosine law gives you angles bigger than 90, whereas sine law does not. So when you're using the cosine law to find that first angle, you always want to make it the largest one. So if we know this side's 4, this side's 5, and this side's 6, which angle is going to be the largest angle and why? Okay, well, the largest angle is always between the two smallest sides. So if you don't remember that, let's write that down. Largest angle is always between the two shortest sides if we're talking about a triangle. So 4 and 5 are smaller than 6, so the largest angle is going to be between 4 and 5. So this angle in here, which is actually nice for us, is going to be theta. Because by the Z pattern, you can see if we find that angle, we also know that angle. It's going to be theta as well, which is the angle between them when they're tail to tail, which we need in order to add them. So that works out good. Won't always be that. You might have to find, say, this angle and then use sine law to get theta. But in this case, we can go ahead and just use cosine law. So again, I'm going to write the cosine law out because some of us might be rusty. So this is the only angle in the cosine law. So if we're finding this angle, we start off our cosine law with the side opposite from it. So if this is the angle I want to find, I want to start off my cosine law with the magnitude of this side. So I'm just going to write that. That's my formula I'm using, but I'm going to start off my cosine law with the magnitude of vector u minus v. So 6 squared equals 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of theta, the angle between the two sides. So what I do next is I'm trying to get theta by itself. And these terms are all multiplying each other. So I'm first going to subtract 4 squared on both sides and subtract 5 squared on both sides. And then figure that out on my calculator. So I'm going to go 6 squared minus 4 squared minus 5 squared. And I get negative 5. And then here, so these terms are gone. I'm going to multiply negative 2 times 4 times 5. So that's going to be negative 40 cos theta. Divide both sides by negative 40. So I know the negatives cancel out. Even the 540 I could reduce to 1 over 8. It's not necessary that you do that, but you can for sure if you want to. So theta is going to be the cos inverse of 5 over 40, or approximately, so the cos inverse of 5 over 40, 83 degrees. So that means this angle in here is 83 degrees. But it also means that this angle here is 83 degrees. So now that we found that angle, we now know the angle between the two vectors when they're tail to tail. So now we can find vector u plus v. So I'm going to move vector v this time to the tip of vector u. Make it parallel and the same length and call it vector v. And then I'm going to draw in vector u plus v. So here's the tail of vector u plus v, and here's the tip of vector u plus v. And now I've drawn in vector u plus v. And this angle here, because I've got parallel vectors, I formed a C pattern. This angle in here is going to be 180 minus 83 degrees, which is 97 degrees. So again, I know the magnitude of vector u is 4 and the magnitude of vector v is 5. The angle between them is 97. So I can use the cosine law to find the magnitude of vector u plus v. So the magnitude of vector u plus v squared is equal to, so the magnitude of vector u, which is 4 squared, plus the magnitude of vector v, or 5 squared, minus 2 times 4 times 5 times the cosine of 97 degrees. So the magnitude of vector u plus v is approximately oops. .8 units. Okay, so sometimes when I do a question like this, I draw my initial diagram and I think the angles are acute, but when I actually solve for angle theta, it ends up being obtuse. Like it ends up being like 110 degrees, which doesn't look anything like my diagram. So usually I just cross that diagram out and redraw my initial diagram so that makes more sense with the angle that I get. But in this case, I was okay. It was pretty good. And remember, when you're finding that initial angle, when you know all three sides, you use the cosine law to find the largest angle, not theta, because if you did have an obtuse angle, you could get the wrong angle for here. Okay. All right, many properties of vectors are analogous to algebraic properties and make simplifying expressions that involve vectors easy. So here's a summary of vector properties. When you're adding two vectors, it doesn't matter whether you add a plus b or b plus a, you get the same vector. If you're adding three vectors, you can find the resultant of two added and then add the third, or find the resultant of the last two and then add that to the tip of the first, or you can just add them each one at a time and your resultant would be from the tail of A to the tip of C. That's what that's saying. This one looks complicated, but it's just a way of saying that if you have 3 times 2A, it's the same as having 3 times 2A, or the same as having 2 times 3A. In the end, they'd all equal 6 vector A's. And this one's the same as saying if you have, say, like 3 times vector A plus vector B, it's the same as taking 3 vector A's and adding 3 vector B's. It's just, there's a lot of algebraic properties that transfer over to vectors. Same thing here. If you have like 3 plus 2 times vector A, it's the same as you can distribute and have 3 vector A's plus 2 vector A's. If you add the 0 vector to any vector, you just get the vector itself. So you haven't changed anything. So it's kind of like adding 0 in algebra, but adding the 0 vector just gives you the same vector. And if you add 2 opposite vectors, you get the 0 vector. And why do we know this? Sorry?
I'm just wondering, like, would you ever use like algebraic variables with the vector or something like that?
Yes. So in second year university, a lot of you will take, depending on what you're in. If you're in engineering, you'll take a vector algebra course, or they'll call it mathematical physics.
Cool.
It is. There's lots of cool math in university. All right, so our next example is just to simplify each vector expression using vector properties. So the first one's pretty straightforward. It's kind of like a flashback to grade 9, so you can collect like vectors. So that simplifies down to 5 times vector x plus 4 times vector y. This one's a bit more complicated, so we can distribute, and collect here. So that's going to be 10 vector u's minus 5 vector v's minus 4 vector v's plus 12 vector u's plus 7 vector v's. And so here's a u, and a u, and v, and v. So we got 22 vector u's minus 2 vector v's. So in the next question is an example of where you might use these algebraic properties. So given vector x is got a magnitude, or sorry, the magnitude of vector x is 5 and the magnitude of vector y is 2, and the angle between vector x and vector y is 70 degrees, find 7x vector minus 5y vector plus 3 times negative 2x vector plus 4y vector, and express the angle as x so many degrees towards vector y. So we can use this idea using our vector algebra here in order to simplify this down so that we just have so many vector x's plus or subtract so many vector y's. So that's what we're going to do. Make this question easier. So distribute there. So if we collect our x's, 7x minus 6x is x vector plus 7y vector. So finding vector x plus 7y is the same as finding this whole thing here. Obviously, this is way easier to draw. So vector x is 5 and vector y is 2 in their magnitudes, and they're 70 degrees apart. So I'm going to draw my initial diagram now. Here's my 5, and here's my 2 at 70 degrees. So this is vector x, and this is vector y. And initially they're 70 degrees tail to tail. And now I want to take vector x and add 7 vector y's. So I'm going to make it parallel and 7 times as long, which I can't quite do nicely, so I'll just pretend that I am. And then draw in my resultant, which is from the tail of vector x to the tip of vector 7y. Make sure you put your arrows on your vectors, and this is vector x plus 7y. And again, since these vector y and vector 7y are parallel vectors, this angle and that angle add up to 180. So if this angle is 70, this angle is 110. And we know the magnitude of x is 5, vector x is 5. And the magnitude of vector 7y is going to be 7 times 2, which is 14. So now we're ready to use the cosine law to find the magnitude of vector x plus 7y. So we're going to say the magnitude of vector x plus 7y squared is equal to 5 squared plus 14 squared Okay, so the square root of 5 squared plus 14 squared minus 2 times 5 times 14 times the cos of 110. 16.397, so vector magnitude of vector x plus 7y is approximately 16.4 units. And I also have to give an angle, so I have to find this expression, which was simplified down to this expression. And this is a vector, because there's no magnitude bars around it, so I have to find the angle. So this is the angle I'm interested in finding, angle theta. So I can use the sine law. So the sine of angle theta divided by the length of its opposite side, which is 14, over the sine of 110 degrees, the angle I know, over the magnitude of the x plus 7y vector, which is 16.3976. And then I'm going to go straight to theta here. So I'm going to do the sine inverse of 14 times the sine of 110 degrees divided by 16.3976, or approximately 53 degrees. And when they ask the question this way, you're going to answer the question they ask. So even though we simplified it down nicely, we're still going to say, therefore, vector 7x minus 5y plus 3 times negative 2 vector x plus 4 vector y is approximately 16.4 units in the direction of vector x, but 53 degrees towards vector y. Okay, we're going to do a little 3 dimensions here. Get us ready for next week. This is just like a little crash course. So we've got 3 axes now because we're going to be in 3 dimensions. So we kind of turn things around. So up and down is going to be our new, actually, let me turn this over or just let me get a blank piece of paper. So up and down is going to be our new z-axis. So this is our z-axis, up and down, okay, z. And to the right is our new y-axis. And then straight out of the page is going to be our new x-axis, okay? So that's how we name that's our new coordinate system that we're going to be using when we're talking about vectors in 3 dimensions. So up and down is z, left and right is y, and out of the page is positive x, and into the page is negative x. Okay, so that's a little bit of a shift there. And you can see that, sorry, the x, y, and z axes are all at 90 degrees to each other in this system, okay? Sorry. So I know you're going to be looking at diagrams that are on a two-dimensional piece of paper, but we're trying to imagine them as 3 dimensions here. Okay, so three-dimensional space. In three-dimensional space, sorry, there's an x, y, and z axis. Okay, the unit vectors that are in the positive x, y, and z directions are named I hat, j hat, and k hat. So here's my x-axis, and you're imagining that coming out of the page right at you. So I hat would be a unit vector, so just 1 unit long in the positive x direction. So that's vector I hat in orange there. Vector j hat is 1 unit in the positive y direction. So to the right, that's vector j hat, 1 unit in the positive y direction. And k hat is 1 unit in the positive, so up in the positive z direction. So first question, state the magnitude of each vector, write it down correctly. So when they're asking you for the magnitude, we're going to use our magnitude bars. So the magnitude of vector I hat, this isn't a trick question. The magnitude of a unit vector is 1, or 1 unit. Okay, so the length of this little I hat vector there is 1. What about the magnitude of 4 vector k hats?
Four.
4, good. All right, now here's the trickier part. What about the magnitude of 3 vector I hats minus 2 vector j hats? Can I just say it like right now? Is it 1, for instance? Yes or no?
No,
No. Why is that?
because you have to use trigonometry.
You do. So in this case, just Pythagorean theorem, but we have to add them tip to tail. So I can't draw in 3 dimensions. So even though 3 I hats would be 3 units out of the page, so it would look like going up like this, I'm going to do it as going down and just label my vector. So this is 3 vector I hats. And then I'm subtracting 2 j hats. Actually, let me draw this on the other side because I didn't realize I was subtracting there. So normally if I was adding 2 j hats, I'd go to the right, but I'm subtracting them, so I'm going to go to the left. So this is negative 2 j hats. And I know they're at 90 degrees to each other because we just showed that with our axes. So I'll do that again. So here's my z axis, my y axis. Here's my other pen. And my x axis is coming straight out at you. So x and y meet at 90 degrees. So this vector that starts at the tail of 3 I hat and ends at the tip of negative 2 j hat is my resultant vector, vector 3 I hat minus 2 j hat. And because it's a 90-degree triangle, we can just use Pythagorean theorem. So we can say that the magnitude of 3 I hat minus 2 j hat squared, because that's the hypotenuse, is equal to the length of this side squared, so 3 squared, plus the length of this side squared, 2 squared. And if I square root both sides, the magnitude of 3 I hat minus 2 j hat is going to be, well, we could do it exactly and leave it as a square root. It's exactly the root of 13, or approximately square root of 13. 3.6. So there's your tiny little intro into when we're going to start algebraic vectors. We'll be working in 3 space most of the time. All right, so that's Friday. The second lesson on forces is not nearly as long. So just some applications. One application, that's kind of where they took some time off in vectors. Normally we would do 3 applications, but they said just to pick one. So I picked force. All right, I'm going to X out of this.
What are the other applications?
Okay, just let me stop recording here.